Welcome back. Today we're moving away from high-level theory and getting into the implementation. We are going to run every core tensor operation live and watch the geometric result instantly unfold on screen. Imagine you're building a house. Bricks are the basic unit. Everything is made from them. In PyTorch, tensors are those bricks. Technically, a tensor is just an n-dimensional array of numbers. Every piece of data we handle, whether it's a high-resolution image, a word embedding, or the weights inside a model, is stored and moved as a tensor. Because everything in PyTorch is built on this structure, our first step is learning how to create and reshape these arrays to fit the needs of our models. We initialize tensors based on the task at hand. Torch.zeros creates a placeholder grid, in this case, 2 rows and 3 columns of zeros. Torch.ones fills that same shape with ones, which is useful for scaling factors or creating masks. We can also generate identity matrices with torch.I, or define a custom arrangement by passing our own data directly into torch.tensor. To see how a tensor is structured, we check its shape. This gives us the exact dimensions. We also check the dtype to see the format of the data, like whether it's a 64-bit integer or a 32-bit float. We can convert these formats using the .to method. Moving from an integer to torch.float32 provides the decimal precision needed for the complex calculations we'll perform later. Simple arithmetic in PyTorch is element-wise. When you multiply a tensor by 3 or square it, that formula is applied to every single cell in the array simultaneously. Matrix multiplication is different. Instead of matching position to position, we use torch.module to rotate and align the rows of one tensor with the columns of another to calculate their dot products. Let's try a quick visualization. If we have a 2 by 3 tensor and we sum it across dimension 0, how many members do you think will be left in the result? Since dimension 0 represents the rows, the tensor compresses vertically. By collapsing the rows, we're left with a single one-dimensional array containing 3 values, one for each original column. These two operations, matrix multiplication and dimensional reduction, allow a network to take thousands of inputs and condense them into a single error value that tells the model how much it needs to learn. Tensors also handle logic. We use comparison operators to filter data by identifying which values meet a specific condition. For neural activations, functions like sigmoid squash any input into a range between 0 and 1. Cautionary tone. There is a common memory trap when copying data. If you simply set b equal to a, you aren't creating a new copy. You've created a reference pointing to the same memory. Change one and the other changes automatically. To save memory, we use in-place operations. Any function with an underscore, like add, modifies the tensor directly rather than creating a brand new one in a different part of your RAM. This is where we gain speed. While a CPU handles tasks one by one, a GPU can process thousands of calculations at once. We move our tensors to the hardware accelerator by calling .to CUDA. For large-scale matrix math, the difference is massive. In this benchmark, the parallel architecture, the GPU, allows us to finish the same calculation hundreds of times faster than the CPU. We often need to reshape data to fit specific layers. Using flatten unfolds a multi-dimensional grid into a single line of values without changing any of the underlying data points. We use permute to swap the order of the axes, and unsqueeze to add a new dimension of size 1, which is a standard requirement for feeding single images into a batch-oriented model. PyTorch also lives within the larger Python ecosystem. We can convert back and forth between tensors and NumPy arrays seamlessly, often sharing the exact same memory to keep the process efficient. This flexibility makes it easy to pre-process data with traditional libraries before moving it into a deep learning pipeline. We've tracked the entire lifecycle, creating the array, setting the data type, performing arithmetic on the GPU, and reshaping the results to fit a model's architecture. If tensors are the words of PyTorch, these operations are the grammar. Learning how they move is the first step toward building something functional. In our next session, we'll look at Autograd, the system that allows these tensors to track their own history and calculate the gradients necessary for learning. Subscribe to stay updated with the series. Real progress in machine learning comes from showing up to refine these concepts every day. See you in the next one.